Your moderator is North Idaho College political scientist Tony Stewart.
Good evening, ladies and gentlemen. On behalf of the panel, it is a privilege to welcome this evening to our program Dr. Woodruff T. Sullivan III. Dr. Sullivan holds a bachelor's degree from MIT and a PhD in astronomy from the University of Maryland. At the present time, he serves as assistant professor of astronomy at the University of Washington in Seattle. He has been on campus today to speak to our student body on the topic, Interstellar Communication, a Plan for Action. During that presentation, and we will also pursue that same subject on this program, such questions as the following were pursued. What is the probability of the existence of any form of extraterrestrial life? If such life exists, how close to our solar system is the nearest intelligent civilization likely to be? How do we best communicate? And will received messages be recognizable? Dr. Sullivan, it's a pleasure having you on our program.
Thank you.
Also joining me in questioning our guests are our three regular panel members. To my far left is Mary Lou Reed. Mrs. Reed holds a bachelor's degree from Mills College and did graduate work in religion at Columbia University in New York City. Welcome back once again, Mary Lou.
Thank you, Tony.
Also back again is Dr. Ken Wright, who holds a PhD in the field of chemistry from the University of Idaho and now serves as chairman of the Physical Sciences Division at North Idaho College and teaches in the field of chemistry. Dr. Wright, welcome back.
Thanks, Tony.
And third, next to me, is Janelle Burke. Mrs. Burke holds a bachelor's degree from the College of Idaho and a master's degree in counseling from the University of Indiana and served for 5 years as Dean of Women at Idaho State University. Welcome back once again, Janelle.
Thank you, Tony.
We'll proceed to questions at once, and the first series from Mrs. Reed.
Dr. Sullivan, your field is certainly a very complex one, and I think we probably should start out with setting the stage and some background. Could you give us sort of briefly some of the different theories about how the universe was created and why we can expect life on other planets?
Wow. I'll do the best I can in a short time. There are many arguments amongst astronomers as to the question of cosmology, which is the study of the origin of the universe as a whole. However, there is a general consensus today, I would say, that the Big Bang theory is the best we have to offer. And in the Big Bang theory, we find that the universe initially was in a very small volume relative to what it is today, and that there was a tremendous explosion in which we are still taking part. And the whole universe is expanding such that it's getting larger and larger, and we are just one part of this. Now, the primary observational evidence for this is that when we look at galaxies very distant from our own, we see that they're all moving away from us. And they are not moving towards us, they are uniformly all moving away from us. And so we therefore say that the universe is expanding. It does not turn out to mean that we are at the center of the expansion, as you might think, because it turns out that no matter where any observer would be, he would see this same picture. This has to do with the fact that light does not travel in straight lines when you look at Einstein's general theory of relativity and so forth. But I don't have time to go into that, but it does not look, it looks the same to all observers. We are not at a unique location, even though we see everything expanding away from us, apparently. And so the idea is that this explosion took place 10 billion years ago. And therefore, we find that the oldest stars are also 10 billion years. In fact, that's how we come up with this number. One of the ways is that we find no stars older than 10 billion years, and therefore we presume that these stars were formed in the very earliest stages of the universe, and that they then coalesce together to form galaxies of stars. A galaxy typically consists of 1 billion or 10 billion or even 100 billion stars. And star formation, however, we find does continue today at a somewhat slower rate than it was in the past, because we can look at other locations in our own galaxy, which is called the Milky Way, by the way. When you look out in the summer night or the winter night and you see a bright band across the sky, that's the Milky Way. And what you're actually seeing is our own galaxy of stars, or a small part of it to be more precise, because the Milky Way is a disk, and we are out at the edge of the disk. is as if you were inside of a plate located pretty much near the edge, and the plate represents where the stars are. Now, if you looked all around you from this vantage point, if you looked up and down out of the plate, you wouldn't see very much. But if you look in the plate, you see a lot. And that's precisely what the band of the Milky Way is in the sky. It's the integrated effect of millions of stars. And so when we look in certain regions of this Milky Way, we see a lot of gas and dust, and we see very bright stars. And these bright stars, it turns out, are burning fuel at such a fantastic rate that they cannot have been burning fuel at this rate for longer than something like 1,000,000 years. Now, 1,000,000 years is nothing, speaking in terms of astronomy, it's nothing relative to the 10 billion years I just referred to. And that means that these stars were formed within 1,000,000 years. And so it seems very logical, although hardly proved by any means, but all the evidence is pointing in that direction, that stars form out of collapsing gas and dust clouds, and that this process of star formation is still going on. And then by looking at other stars, we can find that stars go through definite stages, just like human beings do. There's a definite evolution to stars, that after they form, they burn hydrogen to make helium, and then they expand into a stage we call red giant stage, and then the red giant sometimes explodes, and you're left with just the core of the previous star you had. That's called a white dwarf. And you can have other scenarios depending primarily on the mass of the star. The point is that all of these stages can be viewed if you look at enough different stars in the sky. We only have a snapshot of the universe, and so to find out about evolution, you can't do what a biologist does in a laboratory and actually see what a young animal looks like versus an old animal. Rather, you have to look at many different specimens and try to find a young one and an old one and make the deduction about which is young and which is old and how long they spend in these various stages. And so evolution of stars still continues today.
So you
Dr.
have
Sullivan, excuse me. I think we better interrupt here to get a definition of the different terms you're using: solar system, Milky Way, galaxy, and universe.
Okay. The galaxy I've already defined is a collection of stars. We think there are about 100 billion stars, give or take a billion, in which the sun is just one of these. And the universe is simply that which encompasses everything. And there are billions of galaxies in the universe. And our galaxy is just one of these. Solar system is, as the name implies, it's a system that's associated with the sun, and it's just the system of planets and other debris that go around the sun. Comets is another class of things, asteroids and so forth. It's this system of objects which go around right very near our own star, the sun. The other stars we see in the sky are no different than our star, the sun, except they're much further away, and therefore they appear much fainter. And the size of the solar system relative to the distance to even the nearest star is a factor of several 100,000. And so space is basically empty. There is some gas between the stars, but the stars basically are very isolated. You have to go a long way from one star to another. And yet even within a solar system, you also have to go a long way from one planet to another. And so these objects that we study are sort of isolated oases, if you will, within the vast emptiness of space.
You talk about a non-biological evolution of the cosmic situation itself. What are the chances of biology appearing, of plant and animal life?
Well, this depends an awful lot on what conditions are necessary for life. And when I say life, do we mean life as we know it, or do we mean life in a more general sense? And what is life? All of these questions are involved in that. The trouble is that we only have one example of life. There's no field called comparative biology, right? You have comparative anthropology, comparative sociology, or maybe you don't have comparative sociology since we're all human beings. But anyway, there's no other example of life that we can look at so that we can determine what is in common between these two. What are the necessary conditions to get life, and what is just an accident of the way our particular life has evolved. For instance, we would surely not believe that having 2 ears is a necessary form for intelligent life. It's just an accident that we have 2 ears. It's useful because it enables us to tell which direction sound is coming from better than if we had 1 ear. But certainly some organism that had 3 ears could perhaps even do a better job and could be intelligent, and even one that had 1 ear. The whales themselves may be a very intelligent form of civilization that we don't know about, or at least an intelligent form of life dolphins and so forth, and yet they have no arms and legs, and so that's obviously not a prerequisite. But what is a prerequisite? Must it be carbon-based, for instance? Our own chemistry is very much based on the element carbon. This is what we mean when we say organic chemistry. And is that a necessary prerequisite? Must water be a part of life? And so these are questions which we have no way of answering until we find another example. And right now, in fact, on its way to Mars is a space probe called Viking, which is going to land on the 4th of July, of all dates, 1976, and which is going to send out a scoop. Once it lands, and hopefully doesn't crash, the Russians have already sent 2 or 3 to Mars, and one of them crashed, and a couple others just were not successful. They stopped transmitting after a few seconds on the surface. It's thought that they may have been blown over because there are strong winds on Mars. And in any case, if it all goes well, this scoop will go out and just dig up some soil and bring it inside, and then essentially they're going to try to feed the soil and see if it gives off any waste air, or not air, carbon dioxide, waste gas. And if it does, then this will be good evidence that there might be some kind of life there. There are several experiments that will have to cross-check each other to see whether one believes that there's life there. And even if you get positive results from all experiments, you obviously would want to send other probes and do further studies. In any case, this is our first attempt to detect biology outside of the Earth, and the field of exobiology is come into its own, essentially. As you know, we found no life on the Moon, despite very careful searches, and now we're going to find out if there's any on Mars or not. But now, if we extend the question to, is there life anywhere else in the galaxy, not just in our solar system, well, then you have 100 billion stars, and you need to know what fraction of those stars might make planetary systems, what fraction of those planetary systems might have suitable conditions in terms of the temperature and the density and the constituents of gas and molecules that are on the planet. What fraction of these would be conducive to the possible origin of life? And then what fraction of that life could evolve to different stages that we might be concerned about? So there are a lot of unknowns in this process.
Dr. Wright.
Dr. Sullivan, I'd like to ask a practical question, but one that I think is a little bit philosophical anyway. Give you a chance to defend your profession here.
Okay.
In these days of relevancy, concern for relevancy, and cost consciousness, I'd like to ask you, why should man, the United States in particular, pursue the study of astronomy? It costs a lot to build an observatory and have these powerful telescopes, and you have to pay the salaries of astronomers. What do we have to gain?
That's
Why
right.
should we study it?
My salary is paid by the taxpayers of the state of Washington, and so I'm sure they'll be most interested in knowing what they get out of it. And in fact, almost all of astronomy is funded through the federal government. There's a little bit of private philanthropy, but very, very little, and getting less all the time. The basic answer is that it doesn't help you build a better mass transit system, or it doesn't help you have a better health care system, anything like this. Of course, there are a lot of things that the federal government funds that don't do that also. But nevertheless, I think that the ultimate answer must be that astronomy simply provides a cosmic perspective, so to speak. It enables us to try to understand where our position is in the cosmos. And these are questions that have been asked since the earliest times, and the question is, where do we stand? What is the nature of our planet? Where did we come from? Where did our planet come from? Where did our sun, our star, the sun, come from? And these questions have always haunted men, and I think that's fundamentally what fascinates astronomers. Sometimes one gets in a very narrow field of astronomy, and you get very hung up on a narrow little question, and you miss the forest for the trees. But whenever you can step back a little bit, I think that's really what drives one. It's rather interesting that in newspapers, for instance, if you talk to science editors of newspapers, they say that astronomy is the second most popular science topic in newspapers. The first one is medical science, and for obvious reasons. The second most popular is astronomy, which is just the opposite of medical science in terms of its practicality. And I think that it must be the fascination that people have when they step out and they look at the sky and they say, now where do I fit into that, and what what's going on in that sky. And so there is no practical justification. One can try to make arguments that maybe, it used to be, of course, very helpful in navigation, and therefore kings would give prizes for better methods of navigation using the stars. But I don't think we can really use that justification anymore. People have talked about the possibility of mining the moon and so forth, but I don't really look forward to that prospect. It may not ever be economical, even if it is. I would hope that it wouldn't be allowed, because I don't want to see the moon strip mined or anything like that. In any case, I think it has to be the same justification as for poets, that people enjoy it, and if you want to support poets, I think you should support astronomers and vice versa.
Janelle Burke.
Can you tell us the probability of life in space? What makes us think that there might be other life in space?
Well, it's basically a plausibility argument. You cannot prove it, and we may be all wrong, but all of the indicators that we have about the origin of life, much research has been done in the last 5 or 10 years on the origin of life here on Earth, is that there was no special conditions necessary, that it was simply that the early Earth had the right temperature and the right pressure and so forth. Those, you might call those special conditions, but once you had that, then the elements which are the most abundant in the universe, by which I mean carbon and nitrogen and hydrogen and oxygen, these elements very naturally want to combine into molecules, at first simple molecules like methane and ammonia and carbon dioxide. And experiments have been done, for instance, where you take a flask of material, water, and then you put in some ammonia and carbon dioxide and methane, and then you apply a spark to this mixture for maybe 2 days, and you have just a spark gap for 2 days, and when you then analyze what's been made, you find amino acids. You find them in copious amounts without any trouble at all. And so the question then becomes, now, no one has been able to make proteins in this fashion, although people are making things that are more complicated than amino acids. But it seems like it's a very natural process to go in the direction in which we know are the building blocks of life, that it's not something that requires very special conditions, that it's very natural, the most abundant elements, not unusual conditions, and so forth. And so if this is true, then why should we be the only form of life? And to extend it further, why should we be the only form of intelligence in the universe? Because other stars will have planetary systems. We feel that the formation of planets is a necessary byproduct of the formation of stars. There's nothing special about that either. When a star, the gas collapses to form a star, then you get planets, which are simply bits of star matter that did not coalesce with a star because they were spinning too fast, and then they cool off and become solid, whereas a star, because it's more concentrated to the center, it becomes hotter and stays a gas. And so if planetary systems are the rule rather than the exception, and that's exactly what we think, and if the origin of life is nothing special, if it's a matter of simply of the chemistry of the elements as they're given to us in the universe, then why should we be unique? And that's the basic argument.
Mary Lou Reed.
Well, then let's move into this situation that you were talking about this morning with the students, the possibilities of interstellar communication. Could you give us some of your ideas on how that could be brought about?
Well, if we accept the previous premises that I mentioned, you then have to ask the question of how far away is the nearest advanced civilization likely to be. That's a very important question because that determines on how feasible, now here we are getting to practical aspects, how feasible it will be to actually carry out communication. If you only have a certain power transmitter, it only has a certain range. And if our nearest galactic neighbors turn out to be thousands of light years away, it's going to be very difficult communicating with them. And if they turn out to be only tens of light years away, it will be very easy. And best estimates are that it's somewhere in between, perhaps. So the question of how do we communicate gets to be rather technical. Basically, you want, and also there's another assumption in here which I haven't mentioned earlier, and that is that these other civilizations that evolve want to communicate. Because, for instance, they could be very intelligent and have gotten past the stage where we are. I like to think of us in sort of technical adolescence now. We've only had a technical society for a few tens of years, really. And if we're able to survive for hundreds and maybe thousands or even millions of years, and that's a big if, of course, as anyone who reads the front page of a newspaper knows. But if we're able to get past this very difficult adolescent period, then would we still want to communicate? There's a number of radio astronomers and other people now who want to communicate, but maybe this is just a fad that we have now. So that's a big if. But if they want to communicate, then how would they go about doing it, or how should we go about doing it if we want to try to do it the other way? And when one considers the various possible means, you could try to shoot particles, or you could try to have a laser, or you could try to have radio waves. It turns out that radio waves are by far the most cost-effective. You can send the most information for the cheapest amount of money, and we already have the technology for that. It's not something that's 10 or 100 years away. It's available now. And so it seems like this would probably be the best way to go, and likewise, that would be the best way for some other civilization to go if they wanted to communicate with us. Now you might say, well, they're going to be far more advanced, probably, than we are, and so they're going to have Z-rays that we know nothing about. Well, that may well be true, but if it's true, then of course we'll never pick them up. But if they are really trying to communicate with all civilizations possible, they'll go for the simplest means, and they'll go back to the earliest technology, and that will be radio waves, we feel, if their science develops like ours does. And so the approach that's been taken by the scientists that are thinking about this problem now is that the best thing to do is to use a radio telescope, either to send out radio waves if you're trying to be active about it, or to listen for radio waves if you want to take the passive mode.
Are there any mysteries out there that give you reason to believe that maybe anyone's trying to communicate with us now?
No. The only reason that we think that someone might be trying are the sort of arguments I've been giving earlier.
The plausibility.
The plausibility arguments, indeed. To date, I would estimate that a few hundred stars have been actually listened for interstellar communication of some kind. All results are negative. However, the best estimates that we can make as to what fraction of these stars would be likely to have life is that you have to look to 1 million stars before you'll have a chance of picking up one technical civilization. So we've only begun the very smallest part of this whole task if we want to really give it a chance.
Well, you talk about whether or not they'd want to communicate and how we would communicate, and have you given some thought to what we'd want to say?
What we want to say. That is indeed a problem.
It would have to be fairly significant to go on for millions and millions of light years.
Indeed.
It would take a large committee.
For exactly that reason, that it would have to be rather significant, radio astronomers have shied away from trying to send anything, because it would undoubtedly require a committee of international committee of astronomers, and heaven knows the governments would have to get involved, et cetera, et cetera. It'd be a very official, big brouhaha about this whole thing, of what we're going to send.
Yeah. Something like life is a river.
And so radio astronomers to date have not tried that. There was just a demonstration that was done a couple years ago using a large telescope, but it was only sort of a 10-second message just to demonstrate the feasibility of it. And so the approach has been to listen. Not to try to send, because you see there's another great problem with sending, and that is that it's very unsatisfying from just a personal point of view. If I'm a scientist that wants to set up this project, and so I spend quite a while thinking about what the message should be and so forth, and then I send it, well, what do you do next? You see, you have to wait for hundreds of years for the possible reply, and that's very unsatisfying. You like to have an answer within your own lifetime, at least. We estimate that on these plausibility arguments that 1 out of every 1 million stars probably has a technical civilization. That means that the nearest technical civilization is probably of the order of a few hundred light years from us. And so you see, that means that if we send a message saying how do to them, then it takes 200 years, 300 years to get there. Radio waves travel at the speed of light, and then 200 or 300 years to come back, and then the answer we get back is, what? So then we've got to send the message again, and so forth. So this is a very inefficient way to do it. We expect that the communication would be on a one-way basis, that they would be sending their Encyclopedia Britannica, their Webster's Unabridged, and so forth. And of course, they've got to send us a whole lot of knowledge about their mathematics and their language and this sort of thing. There's another interesting aspect of this, though, that's fun to think about, is that although we have not purposely sent messages, we are inadvertently sending messages all the time. And that comes from the television and FM broadcasting, which we are doing in copious amounts all the time. This radiation ideally goes into homes, as it is now. Channel 7 has a broadcast tower on some mountain or on a tall tower anyway, and they try to send their radiation out along the horizon so they can cover the maximum amount of homes. But you can never design a system perfectly. The engineers try, but they can't do it perfectly. And some of this radiation goes up a little ways. And it only has to go up very slightly, and it misses the Earth entirely and goes out into space. It's not blocked by the Earth's atmosphere. And so, the net effect is that we are sending out television and FM broadcasting inadvertently. And you can think of this as a bubble around the Earth, an expanding bubble, which moves out at the rate of 1 light year per year, because that's the speed of the radio waves. And this bubble is now 30 light years in radius, because we began a significant amount of broadcasting about 30 years ago after World War II. And what do we find if we look at the forefront of this bubble? We find things like Howdy Doody and Milton Berle, the Army McCarthy hearings, other things like this, which are supposedly signs of our advanced intelligence to anyone that might pick them up. And later on, further in from the bubble, you will find later programs that have been emitted in the last few years.
Star Trek. Yeah.
Star Trek, right, and Welcome Back, Kotter, and other signs of our intelligence. It'll be a much higher power level because we have much more radiation in the past few years. But it turns out that it's highly unlikely that anyone will pick this up. It's very weak. It's so attenuated by the long distances it has to travel, and it's so unlikely that one of the nearest stars within 30 light years would have an advanced civilization that, very fortunately for us, no one's probably picking it up.
It might assure that they didn't want to communicate for sure.
Right, that would turn them off entirely, probably.
Dr. Wright.
Excepting this show, of course.
Of course. Well, you just began to answer one of the questions I was going to ask about what's the probability that some of the communication that we've already transmitted has escaped from the Earth and might get out there. You pretty well covered that. What you're really talking about then in interstellar communication is a concerted effort.
Indeed.
And essentially to beam this radiation in a particular orientation to try to get it to a particular part of our galaxy,
well,
for example.
The concerted effort is more to listen than to beam it out, for some of the reasons I've stated. Because it appears that probably if civilizations last for millions of years, technical civilizations, and we've only been around for a few hundred years, then we're probably just about the dumbest ones in the galaxy. You see, we've just started. It's far more likely that all of them are much more advanced than we are. And so it's a much more profitable exercise to try to listen than to send out. And in general, it's better to keep our mouths shut also, like as you were implying. And so the idea would be that they could harness much more power than we can, and therefore communicate over larger dimensions, and therefore it'd be more likely that we'd pick them up. And so one proposal called Project Cyclops, which was studied by NASA a few years ago, and it has not been funded, I should add, but it was a feasibility study was made, was to build an array of 1,000 large radio antennas, each one 300 feet in diameter, the size of a football field. 1,000 of these things would be several miles in diameter circle. It would be an incredible thing to see. And that this thing would search each of the nearest million stars for about 1,000 seconds each, trying to detect a signal, so they'd all move to the next star and so forth. And a little bit of calculation will indicate that to cover 1 million stars at 1,000 seconds per star would take you about 30 years. So it's still a very long-term program. It would cost $10, $20 billion, depending on how fast the price of steel is going up, because that turns out to be the main cost of this thing. It's not to pay the astronomers' salaries or for the computer electronics. It's just the plain cost of steel for these 1,000 antennas. And this has been one approach that is thought would have a reasonable chance of picking up intelligent signals if indeed our plausibility arguments have any merit to them. But it's rather interesting to think about what happens if we get a null result. If we actually carried this out and got no answer, it would still be a very significant result, I think, because it would make us realize how unique our own form of life here is on Earth, how precious it is, and it just might make us stop trying to harm each other and maybe work together a little bit more on this planet. On the other hand, if it had a positive result, of course it would be have incredible implications for all sorts of things, because we would realize that we are only one of many civilizations, and irrespective of the information that we gain from this, I mean, they might have all sorts of information that can tell us how to avoid nuclear holocaust and solve the food problem and all this sort of thing. Irrespective of that, the very knowledge that there is some other civilization, I think would change our views. We'd realize that we have a lot more in common than we really have differences. So either way, it's a very exciting prospect to actually think about carrying out such an experiment.
What about the possibility of using lasers if we do decide to send a message instead of just to listen?
Or you could turn the question around and say, why don't we look for lasers from other civilizations? Well, it turns out that lasers are just not cost effective, that you cannot send as much information with a laser, which is simply a beam of light, than you can with radio waves. And another problem is that light waves, there is dust between the stars, smoke-like particles, and the distant stars are not visible to us for this reason. All the stars that we see are pretty close to us, because the light is absorbed by this dust and reflected by this dust, and the same way would happen with lasers. But radio waves go right through. And so the radio waves essentially, just like they go through fog here on Earth when you use them for radar, and so the radio waves are a better medium, it's thought.
Janelle Burke.
NASA's sending Pioneer 10 into space.
Right.
I wonder if you could tell us what is different about Pioneer 10's venture into space.
Right. The Pioneer 10 was a spacecraft that went to Jupiter and took many fantastic close-up pictures of Jupiter. You may remember in the newspapers a year or two ago. And actually there was a follow-up satellite, which was virtually identical, not satellite is not the proper name really, a probe called Pioneer 11. And the unique thing about these two probes is that they are going to leave the solar system entirely. All the other probes that we've sent, flybys past Mars and Venus, once they've done their job, they simply go into orbit around the sun and become, as it were, artificial planets. But Pioneer 10 and 11 are different. First of all, these planets are well outside of us. In order to get these probes there, we had to give an awful lot of energy to them. And in the process of doing that, they will just escape the sun entirely. And so it was thought that in a gesture for this, that we would put something on this spacecraft which would show where it came from and when it was launched, and this sort of information, in the very unlikely possibility that some other form of life or organism might pick it up. They might be tooling around the interstellar regions and just find this bit of flotsam there and say, now what is that? And they'd take a look at it, and this would be maybe a bit of a Rosetta Stone that they could figure it out. Now, it's very unlikely that this would happen. I think really the more significant thing is the gesture that was made. And the plaque itself, which you can see on your screen now, was made up in 2 or 3 weeks. And so there was not really much time to put a whole lot of thought into it. And if they were going to do it now, the people that made this up, Carl Sagan and Frank Drake of Cornell University, they would undoubtedly do it in a very different fashion. But here you see the plaque. And on the right-hand side, you can see that there are 2 organisms, which we're rather familiar with. One organism has its right hand, or its right appendage, to be more general, raised in a sign of goodwill. This was the idea anyway. Of course, some other civilization might take this as being a sign of hostility for all we know, but anyway, that was the intent. They're not holding hands because that was felt that the whoever picked this up might interpret that as being one organism then, one large organism with 8 appendages rather than 2 organisms. And in back of them is a line drawing which represents the spacecraft. And so you can get the relative size of the organisms to the spacecraft from this means. Down on the bottom is a representation of the solar system, showing our sun on the left and the 9 planets going to the right from the sun. And you can see that the trajectory of the spacecraft is indicated starting on the 3rd planet from the sun, namely the Earth, and then moving out past the 5th planet from the sun, which is Jupiter, and then past the 6th, Saturn, which is indicated with its rings around it. And then the spacecraft is going off into the interstellar regions. The star-like thing, which dominates the left side of the plaque, is designed to show the location of our sun relative to nearby stars. And it does this through using pulsars. Now, pulsars are natural rotating stars, very small, dense stars, which give off radio waves, radio pulses, very precisely every 1.237 seconds or 0.897 seconds, depending on which pulsar you're looking at. They're very accurate clocks. And the idea is that they act as beacons they're natural beacons in the sky, or buoys, if you will, and that by showing where our sun is oriented relative to the nearest 15 pulsars or so, that we can indicate where our sun is, and that they can then trace back where this thing came from. Now, this plaque will last for several 100,000 years before it becomes pitted up by this interstellar dust I was talking about, and it's highly unlikely it will be detected by anyone else, but it's our first gesture at interstellar contact, really, and so for that reason it's significant, I think.
Dr. Sullivan, I'd like to ask a question in relation to the travel within some of the galaxies. Oftentimes when we interview people on this program that are dealing with something in this area, they tend to assume that all civilizations that exist, if they do, have no more technology than we in travel. Is this a false assumption? In other words, is it possible that some civilizations are so advanced that they have been able to intellectually conquer the problem that we have not, and that is the question of travel, space, and time?
Well, if you phrase the question as, is it possible? Yes. I refuse to say that anything is impossible. One would be foolish to do that from a historical point of view. If you go back 10 years or 100 years or 1,000 years and find out what people would agree on as impossible, then they look very foolish indeed later on. And so it is possible, but we can only work within the realm of science as we know it. Because once you allow yourself to go outside that boundary, well, then anything goes. And then nothing can be established one way or another. The nature of the scientific game is to work within a given boundary and to see where that leads you. And if you're willing to say that star X has an entirely different physics than we do, well then, of course, anything can be happening there. But it's not a useful assumption, because how am I going to know whether to believe person A's version of the physics on star X or person B's and so forth? And in fact, all the indications we have in astronomy are that the physics and chemistry of the stars in other regions of our galaxy and other galaxies and other parts of the universe is the same as what we have here on Earth. And that's very comforting, and that allows us to in fact, usefully carry out astronomical research. But as to the question of whether it's likely that other advanced civilizations would be traveling faster than the speed of light or this sort of thing, it's really something that we cannot know. We can only say that we think it's improbable based on our understanding of physics. And until we have some evidence otherwise, we will say that it's not profitable to pursue that as a likely possibility. And even if we talk about traveling at less than the speed of light, which we know is possible, it turns out to be very inefficient, very, very expensive, and it takes a long time. You realize that if we had something like the Saturn V rocket multiplied by 100, I mean a huge rocket, that it would still take tens of thousands of years to get to the nearest star, let alone to investigate the nearest million stars to find out which one might have life. And so that's just not the way to go. It's much more efficient to send messages via radio waves or some other technique than to actually try to go and visit and shake hands.
In connection with this topic, I'm sure that in your lecturing that you're constantly asked your views on UFOs.
Yes. Well, I'm not any more qualified really to answer the question of UFOs than someone else is in another scientific field, because we don't know that they have anything more to do with astronomy than they do with meteorology, or that they do with chemistry or anything else. A UFO, it stands for unidentified flying object. That means it's something in the sky which we don't understand. And heaven knows there are lots of things that we don't understand. We don't understand how to predict the weather for tomorrow, let alone these things that are going around the sky. Now, first of all, when one does an intensive investigation of most UFO sightings, you find that it can be explained, that it's either a different kind of plane than the person has seen before, or it's Venus when it's especially bright, or this or that, to the aurora or something like this. But there are other cases where there are many reliable witnesses who have seen an atmospheric phenomenon of some kind called a UFO, and they cannot figure out, scientists cannot figure out what it is. And so I see this as a very interesting area for pursuing the research, but it really shouldn't be asked any more on this show than it should be asked on any other show that you might have with a scientist. You see what I mean? What does it have to do with extraterrestrial intelligence? Now, I know that there are some people that believe that the UFOs are spaceships and they're visiting us and so forth, but this is the explanation of very last resort, as it would be the explanation of very last resort for anything that we might find that's unexplained. Now, also there are reports when a person says that a Martian landed in my backyard and got out and picked a tulip and went back in and flew away, and then you ask the neighbors if they saw it and they didn't see it. So there are no reliable reports with many independent witnesses of anything that can be called extraterrestrial civilization. There are reliable reports of unidentified phenomena, but these most likely are some sort of astronomical or atmospheric phenomena which we just don't understand. And I'd be the first to admit that science says a lot of things we don't understand that are quite natural and not due to extraterrestrial intelligence.
Well, are you optimistic, Dr. Sullivan, that man is going to take good enough care of this planet to give time for interstellar communication?
Yeah. Well, that question bears very much on the possibility for contact, because obviously if we blow ourselves up in the next couple decades, we're not going to be able to have the chance to search enough stars to do this. And more generally, the question is, how long do technical civilizations last? If each of them only lasts for 10 or 20 years, then there's going to be far fewer number of them in the galaxy than if each of them lasts 1,000,000 years. And so this question you raise is very relevant here, and unfortunately it's the same problem as the biology. We only have one example of a technical civilization, and it's very hard doing statistics with one, although some people try sometimes. And so the question is, what is the average longevity of a technical civilization? And I might add that the estimates that I was making before, that 1 out of every 1,000,000 stars might have a technical civilization, were based on the fact that the average civilization would last for 10 million years. So that's sort of an optimistic view. But that doesn't say that everyone lasts for 10 million years. You see, to get an average of 10 million years, it could be that 99% of them only last for 100 years, and the other 1% last for 1 billion years. And then if you take the average of 99 100s and 1 billion, you'll find that the average is 10 million years.
Well, the proposal resurfaced in the newspaper the other day to use space as a depository for nuclear waste. Now, do you have sort of an organized forum in which astronomers can oppose this kind of thing, or is that not really in your field?
Well, there are organizations, indeed. This has happened before. This is not the first time. For instance, 10 years ago, the Air Force wanted to send up needles, essentially. They sent up a rocket, and the rocket was going to release needles that would cover a large part of the Earth's atmosphere, and these were going to be used for communications. You'd be able to bounce radio waves off these needles just like you could if you had a big flat sheet of metal up there. Well, radio astronomers were aghast at this because these needles essentially would not allow natural radio waves in from the radio sources that we make our livelihood from. And so they opposed this project very, very much. And in fact, a small-scale version of the project went, but the grandiose plans were scrapped because of the protest. Another example of this sort of thing is optical astronomers are always fighting light pollution, as they call it. The fact that cities are always growing and you're trying to keep down the amount of light because you're trying to look for incredibly faint things. Now, in this example, what would it mean if you tried to dispose of nuclear radioactive materials outside of the Earth? It would make space radioactive, and if these things got near Mars or the Moon, that would make Mars or the Moon radioactive, and it would completely destroy the natural, as it does here on Earth, no differently, the natural state of the planet, and it would make it that much more difficult to figure out what really formed these planets and what makes them go. They have their own geology, just like we have our geology, and it would be a great shame from a scientific point of view. Although, if nuclear reactors turn out to be the best alternative for our energy needs, and I'm not so sure about that, but I'm not really qualified any more than you are to talk about that, then maybe this is the best thing to do. Maybe it's better than burying them in salt mines, and it would be just the least lesser of all the evils that we can think of.
Well, do you astronomers keep in very close contact with each other in terms of stellar communications?
Well,
are you
I should
communicating
add that
on
this is a
the
very
planetary level?
Yeah, that this sort of problem is very new. It's only been considered really seriously for the last 5 or 10 years, and there's only a very small fraction of astronomers that are worrying about it. Like, for instance, in the United States, there are probably 2,000 astronomers. It's a very, very small field, and therefore astronomers do know each other very well. Of those 2,000 astronomers, perhaps a few dozen are really spending much time thinking about interstellar communication. The rest are doing studies of stars and galaxies and planets. Very exciting stuff, but perhaps doesn't quite capture the imagination like interstellar communication does. And so that indeed, if there is a project of this kind or some other threat, there are appropriate ways to protest to the Congress or to the government in whatever way you might think appropriate. But then, of course, astronomers become one lobbying organization, and you perhaps no different than other lobbying organizations, and a congressman has a hard time sifting out which is which.
Dr. Wright.
Dr. Sullivan, I've got to ask you a personal question here. Do you personally feel that we have anything to fear if there are other civilizations and we do manage to establish communication with them? Do you think man on Earth has anything to fear?
Well, once again, if you say, is it possible, the answer has to be yes. Whenever one enters into any venture, be it getting married or building a house or anything, there's a risk. And if you want to avoid all risks, then you tie your hands and you sit down, you do nothing. And so there is a risk, and how much of a risk it is, your guess is as good as mine. I would say that the likelihood is that there is very little interstellar travel for some of the reasons I mentioned before, that it's just very expensive. And but then maybe we cannot imagine the resources that other societies could bring to bear on the thing, and they really do it. But it seems like interstellar communication is really the feasible way to go, and that therefore societies would be transmitting information back and forth. It would be like a network of libraries. In fact, we are developing this in the United States now. All libraries are connected up with other libraries by teletypes, and if you don't have a book here, they'll transmit passages from the books and this sort of thing to the other library. And that's what it would be like. A great community transmitting information, but no threats of attack or anything like this. That is the view that I would take.
Janelle Burke.
Your particular field of expertise is radio astrology,
Yes,
as I understand.
astronomy.
Astronomy, that's quite correct. And I wondered if you could tell me, where are your observatories in Washington?
Right. Well, the University of Washington does not have its own radio observatory, but does have an optical observatory located on Manastash Ridge outside of Ellensburg. And in fact, we have open houses often. There's one on the 4th of June. You best double check that date by calling the astronomy department of the University of Washington if you want to go. But I'm quite sure it's the 4th of June. And these are open houses where the public can go up to the mountain on an evening and look through the large telescope. It's a 30-inch diameter telescope. It's primarily used for training graduate students. When one wants to do advanced research projects, we go and use the national observatories, which are located near Tucson. There's a Kitt Peak National Observatory, and there's a Southern Observatory, because you cannot see all of the sky from the northern hemisphere, which the United States operates in Chile, called the Cerro Tololo Inter-American Observatory. And we can also use other large telescopes that are run by the University of California and so forth. Now, I'm a radio astronomer, and likewise, I have to go and use the large national radio facilities, the National Radio Astronomy Observatory in West Virginia, Arecibo Observatory in Puerto Rico, and so forth. And it's just getting to the point where it's just too expensive for each university to be building its own telescope. We have to pool resources and have national facilities, essentially. And then you go for maybe a few weeks a year and observe. You come back and you spend the whole rest of the year trying to understand the data and publishing reports about it and so forth.
Where are other great observatories throughout the world?
Throughout the world, well, the largest telescope in the world is right down outside of San Diego, the Palomar Observatory, although the Russians for over a decade now have been building a yet larger one. The one near San Diego is 200 inches in diameter. The Russians are building a 5-meter telescope, 6-meter telescope, which is about 236 inches. But they appear to be having troubles because it just hasn't gone into operation. They keep saying next year. Nevertheless, that's going to be a very large operation. Other large ones are in Australia because of the advantage of the southern hemisphere once again. England has just built a large telescope in Australia. For obvious reasons, you don't want to put it in England with the bad weather. And Chile has several other large observatories besides the one I mentioned. So I would say the United States, Chile, and Australia are probably where most of the really large telescopes are.
Dr. Sullivan, I cannot resist this question. It's a very personal one for you, and it's not very scientifically based. And that is, since you have spent so much time talking about that the possibility of interstellar communication being most slim and in any time in the foreseeable future, that you have, and also you've given much time to this study. What happens after death? Will there be a possibility that one will have an opportunity in some other way or some other life? Or what is your view on death?
Well, I think I'll pass on that one. I really think anyone could give as good an answer as I could on that. That's just outside of my realm.
Mary Lou Reed.
Well, you see, you've opened up our whole occult bag here, and Janelle inadvertently mentioned astrology, and I will mention it advertently, because you've dealt with UFOs. I'm sure you have to deal with astrology all the time.
Yes.
And why is it there are so many of us who would like to believe?
Well, I'd really like to know the answer to that one. I wish we could get an astronomy column in every newspaper as much as we have an astrology column.
Is there any reason why, in your mind, why this has lasted over the centuries?
I think that it's partly to do with what I was mentioning earlier, namely that man does feel like he's connected with the heavens. He does feel a part of the cosmos. And perhaps we're feeling it even more now as we do scientific research on the cosmos, but even ancient man, which of course is where astrology began, must have felt a strong kinship with the groups of stars and the sun and the moon and the planets and so forth that he saw. And that therefore, he obviously made myths about these stars. We have all of the Greek myths, the Pleiades and Orion and so forth. And that also he felt that his destiny was tied in with the destiny of the stars. And basically that's what astrology is saying, is that according to the circumstances of one's birth and so forth, that the stars are influencing what happens. And I would certainly argue that our fates, in the general sense, are intimately connected with the stars, because if the sun for some reason decides to turn off tomorrow, then it's all over very quickly for us. And eventually, the only reason we are here is that the sun was formed and that planets formed in the process and that life evolved and so forth as I went through. So in that sense, our fates are definitely tied with the stars, but there is absolutely no scientific evidence whatsoever that the precise circumstances of one's birth have anything to do with what one is going to, or I should say the positions of the stars at one's birth has anything to do with what is going to happen during the rest of one's life.
I have another personal question. Geologists always seem to have a wonderful sense of time. Do you find that astronomers also have a different kind of world perspective because they are dealing in, it's hard to keep your ego up, I think.
Well, it is similar to the geologists. They dig down to go further back in time, and we go out to go further back in time. Although it's funny, because astronomers, you might think, would really have much more of that perspective, and I suppose they do on average, but the great majority of days as an astronomer are spent working with a paper and pencil and working with these big numbers and so forth, figuring things, and you don't stop to think about what you're really working with. It's only once in a while that you step back, perhaps while you're taking a break observing and you glance at the sky, that you really think about what you're doing, and then it really is an incredible profession to think that you're gathering in these photons which left this star thousands or even millions of years ago, or this galaxy, and that they've been traveling through space all that time, and you just happen to have put a telescope at the right place to intercept them, and then you're going to try to figure out what's going on out there. That is rather mind-boggling.
Right, because it is so enormous.
Dr. Wright.
Dr. Sullivan, there's several technical topics I would like to ask you about, but there isn't going to be time. I was curious about black holes, but I really have a suspicion that black holes are not that significant except in a technical term. I don't think that maybe our listening audience is as much concerned about that. Instead, I'd like to ask you about infrared astronomy. You are a radio astronomer, and you said that makes up a very small proportion of all astronomers. I've got in front of me here a book review called Infrared, the New Astronomy by David A. Allen. And naturally they're touting the book, and they claim that infrared astronomy really has an awful lot to offer and hasn't been investigated seriously since until about 1960. Yet you feel that the way to go on interstellar communications is radio communication. What do you think the value, for example, of infrared astronomy is, and
Well,
why aren't you in that field?
Yeah, what you ask brings up the whole general question of, for thousands of years, optical astronomy, namely what we can see with our eyes, that was astronomy, right? It's either with your naked eye, or then once we had telescopes beginning in the 17th century with Galileo, then you were still looking at the visible light waves. And yet the electromagnetic spectrum has far greater breadth, and it extends all the way from very short wavelengths, the gamma rays and the X-rays and the ultraviolet radiation, then the visible radiation, and then you have the infrared, which is the longer part of longer than the visible waves, and then finally the very longest waves of the radio. Now, in the last 10 or 15 years, all of these fields, besides the visible, have just blossomed because of new technology, because of rockets and satellites. A lot of this radiation doesn't get through the Earth's atmosphere. You must send up a rocket or a satellite or a balloon. And that's why, of course, it couldn't be done. The radio waves do come through, and we are able to do ground-based radio astronomy. All of them give us different information about objects out there, sometimes objects we didn't even know about before, sometimes entirely new views of objects which we did know about before, like stars. And it turns out that the temperature of an object can be deduced by looking at what wavelength it gives off most of its radiation. If it gives off most of its radiation in the infrared, then it's a cool object. If it's most of it in the visible, then it's mediocre. If it's most of it in the ultraviolet, it's a very hot object. And so you can't say which one is better or worse. They all are complementary to give you a total picture of the universe around us. And this is really what's made astronomy take off, I think, in the last 15 years, is this whole expansion of the electromagnetic spectrum. And we get an entirely different view of the universe than we had when we only looked with our eyes.
Janelle Burke, 1 minute.
Are great space catastrophes possible?
What is that?
Are great space catastrophes possible? In other words, the whole solar system would just suddenly stop.
Yes, if the sun exploded, this would
Is that impossible?
This would do in all the planets. On our present ideas, we think that it will go along as it is now for another 5 billion years. It's in its middle age, and it's got a long ways to go. But there are stars that explode. There's no doubt about it. We don't think the sun is one anywhere in the near future. But we can see in other stars that definitely explode and become tremendously bright. Some of the viewers may have seen the new star in Cygnus last September, which was a nova, an exploding star that happened in the constellation of Cygnus.
With that, I'd like to bring our program to a conclusion, and on behalf of the panel, it's been a great pleasure having you on our program, and I know it's been most informative to the viewers.
Thank you. My pleasure.
I thank the panel, too, for outstanding questions. Ladies and gentlemen, join us again next week at 6 o'clock, and until then, good evening.
The North Idaho College Public Forum can be seen at this same time each week over this station. The preceding student production was brought to you by videotape recording.